Yeah, thank you for the introduction. Thank you for inviting me to report on our project from last year. And thank you for organizing the series of workshops last year. 1 year later, I do think that at least I have got a better understanding on what things from machine learning we can try to adapt to our math research. But of course, we keep learning, therefore the reunion workshop. And thank you everyone for being here to listen to the talk. All right, so I will report on a project that did start to one of the number theory workshops here at CMSA last fall. And we wanted to see if we can predict what are called Euler factors of elliptic curves using various machine learning techniques. Okay, all right, let's see. Because this is not just a number theory audience, I'm going to be fairly light on the number theory details, but let me introduce to you an object called L functions. And the most known L function is the Riemann zeta function. It's generally known as an infinite sum, 1 plus 1 over 2 to the s, 1 plus 1 over 3 to the s, etc. Now, of course, the sum only converges if s is large enough, or if the real part is greater than 1. It can also be written more interestingly as a product over primes, which is what we call an Euler product. And the individual parts are Euler factors. We'll see for elliptic curves, these Euler factors look a little bit different, and that's kind of what we're trying to predict. Now, the Riemann zeta function can, even if it is as an infinite sum, is only really defined on just half of the complex plane. We can really continue it to the whole complex plane, except for a simple pole at s is equal to 1. And in this very nice illustration by Neuberg, Meyer, and Schleich, we can see the continued Riemann zeta function. It obtains what are called some trivial zeros on the at the even negative integers, but it also gets these non-trivial zeros at the line 1/2. Right, and this is the Riemann hypothesis that states that all of these non-trivial zeros are exactly on this line. Now we can take this Riemann zeta function and modify it with a few very nice factors here, and then it satisfies a functional equation. Now I'm saying all of this because general L functions will behave very similar to the Riemann zeta function, as in we can define them as infinite sums when the sum converges. They also have these Euler factors, and we can continue them and get functional equations as well. Now, sources of these L functions are various mathematical objects, especially from number theory, including number fields, but also geometric objects such as elliptic curves. Okay, so these L functions are products over primes, and these are those Euler factors. And for elliptic curves, these Euler factors at pretty much almost all the, well, at all but finitely many primes, these Euler factors look the following way, and the APs are those quantities that we try to predict. So elliptic curves are geometric objects. You can describe them as solutions to certain equations, given here in Weierstrass form. So if you're taking the solutions over the complex numbers, you get a donut, which is nice. But here we have some illustrations for solutions over the real numbers. As number theorists, we are interested in solutions over fields like the rational numbers, other number fields, also finite fields, etc. So for example, the AP values, these traces of Frobenius, are defined as p plus 1 minus the number of solutions of the equation defining the elliptic curve over finite fields. So we get a 1 AP for each prime, right? There's infinitely many primes, so technically you have these infinite sequences. Now, obviously, we cannot input an infinite sequence in a computer, but there are theorems that tell us that we don't really have to. A finite number of these traces of Frobenius will determine all others, but to be able to predict the next one, generally, if you're not really assuming anything like the generalized Riemann hypothesis, you might need, excuse me, you might need a lot of these AP values. So what we set out to do was try to see how much information we can extract from a fairly small sample of the AP values to predict the next one. We also kind of did that just because, right, we had constraints in terms of resources. So we try out something smaller, and then if it works out, then we might try to scale it up. So our goal was to predict AP of E given the previous or nearby values. So one of the main experiments that I will report on was trying to predict A97. So that's the 25th prime. So that's the trace of Frobenius at the 25th prime, given 24 previous values. So A2, A3, A5, all the way to A89, one for each prime. And in theory, as I said, yes, we should be able to predict that. In practice, we're still trying to figure out just how many values we need to input. So for those of you who were here at the workshops, one of the things, right, we got access to all of these new tools and sort of new toys in a way that we wanted to see, okay, well, how do they perform when we apply them to different data sets? And there's a lot of data sets in number theory and other fields. For us, it was especially interesting to try to apply these models to data in the LMFDB, or the L functions and modular forms database. One of the data sets there is a data set that contains all isogeny, or what are called isogeny classes of elliptic curves. So basically, in one way, each training example was kind of one elliptic curve, right? Generally, I believe we have like, are the data sets complete up to like 10 to the 8th or? Okay, not complete. Okay, yeah,
Most of them are there.
Most of them are there, right? So generally, there are data sets with elliptic curves with ordered by what is called the conductor up to 10 to the 8, and that contains about 20-something million, if I remember correctly, elliptic curves. Those were very big data sets. We restricted ourselves to those elliptic curves with a conductor up to 10 to the 6, and that was about 3.6 million elliptic curves. Although for one of the experiments later on, we did have to expand to conductor 10 to the 7. So okay, now this is a fairly kind of curated talk. The process, as you know, is never really linear. So we actually kind of tried to do something else first, and then we kind of went to try to predict the exact value A97. Right? Basically, we did a few other experiments earlier on. We tried to predict A97, modulo 2, right? That's coming from the theory of mod L Galois representations that tell us that, well, if you want to predict the whole value, you really kind of just need to predict it at, different primes, and then you can patch things together. And those kind of worked out. So then we tried to predict the whole value, right? And then ultimately we wanted to see, well, if the experiments are doing well, can we figure out maybe what they're doing? So we'll see some of the conclusions that we've made. The code is available on GitHub for most of the stuff that I talked about today, at least everything that we have in the article that was recently accepted. Yes, please.
Is it because you're limiting the conductor to some bound that it should be possible? Because naively, I would have thought that if you let the conductor go to infinity, you really look at all the elliptic curves, then the Chinese remainder theorem would kick in, and it would tell you that all the APs are basically independent.
Yeah, exactly. Yeah, so
it's because you're looking at, okay.
Yeah, it's kind of, right? When I give this talk, sometimes I say, well, if you know that a number is divisible by 2 and divisible by 3, that tells you nothing about whether it's divisible by 5, unless you know that that number is between 1 and 10, right? And then you kind of know that. So that's kind of similar. If you're bounding the conductor.
Well, let me follow up on that question, because what it suggests, there would be 2 limits: the limit where you put more and more curves and increase the maximum conductor where you lose all predictivity. And then conversely, the limit where you take more and more APs and try to predict more and you gain predictivity. So there should be some sort of a combination or ratio or scaling quantity that controls how predictive you can be.
Yeah, and something else that we ran into was you also need big enough data sets. So, right, yes, we have 3.6 million elliptic curves, so that was fine and dandy for what we were doing. But then when we were looking at, when we were, inputting the AP's mod 2, suddenly these 3.6 million training examples became a few 100,000. So it's like, oh, okay, we need way more, because the mod 2 Galois representations were way fewer than the elliptic curves by themselves. So initially, okay, very naively, I was thinking, well, we have 24 different primes, 2 to the 24, that's like a few million, way past 3.6, maybe we'll have enough. We did not. So we did have to increase our conductor to look at the mod 2 experiments up to 10 to the 7th, but then it felt like we didn't have enough APs because the performance of the models got worse, way worse. Yeah. So.
Or you could even quantify perhaps this dependence. There should be some combination of number of APs and maximum conductor that controls how predictive you can be.
Right, there are different bounds, right? So like one of the stricter bounds, I think, is like the storm bound, right? But that's probably way more than you really need. And then there's different bounds based on, assuming the Riemann hypothesis and whatnot. So, but I guess we're still trying to figure out, well, what works practically. Yeah. Sorry, I forget. Did I answer your question?
Yeah.
Okay. All right. So we tried a few different models during the 2 number theory workshops. So the first workshop focused more on traditional methods like neural networks, and we did try a few neural networks as well for this experiment. The second model that we used for most of the experiments was a transformer model, as was implemented by François Charton. And basically, we didn't really try too hard to optimize all the parameters and try to get the best, performance out of our models. We wanted to get something that looked like, it was learning to predict things, but we can't necessarily claim that it does as well as the model could do. So a bit of a refresher on transformer models. Basically, the inputs are the AP values, which are integers, okay? But it doesn't treat them as integers. It really treats them as kind of strings or like their own words. And as the model keeps training and learning, it also learns to embed these words or tokens, those numbers, based on relationships it learns from the data, okay? So what we input are, the tokens or words describing the APs, the integers, so there's fairly few of them. When we're predicting A97, it goes between -19 and 19. So that's like 39 tokens, not much. And there's a few special tokens, but it's not that much. So usually you have, for the LLMs that, are used for GPT and whatnot, you have a very large number of tokens. So you have a very big space, R to the number of tokens, that then gets condensed into a way smaller space, R to the D. In our case, we just kind of use the default. So actually, the dimension D was 256, which is way bigger than we even really needed. Then there's a few different attention layers, a few feed-forward neural networks. For the default that we used was 8 attention heads and 4 transformer layers. So 4 transformer layers, each of them with just 1 hidden layer. But all of these are parameters that you can play around with. Okay, and then after that, it embeds back into R to the number of tokens, and then using the softmax, it tells you what's the next token that it predicts, that it says it's most likely to be the next one. Okay, so that's the encoder, an encoder-only transformer model. We did play around with encoder-decoder transformer models, but there the architecture is a little bit more complicated, and we didn't necessarily need something, much more complicated than this. The performance was very comparable. All right, so what were our input sequences? For the experiment for predicting A97, we input sequences. I'm saying of length 24, but we had plus and minus tokens as well. So technically, I guess length 48. So one for plus minus and one for the absolute value. All right. And then the output was try to predict A97. Right. So there's 39 options there. The most common value was at plus and minus 2, at about 8.4% of the data. All right. So this is kind of a visualization of, it's almost like a confusion matrix, but I realize that it's actually flipped. Usually the predicted value is on the x-axis and the true value on the y-axis. But a few observations. The model did better than kind of the default. So it didn't just guess things at random. So the most common class was at about 8.4%, right? The accuracy of the model was about 53%. So it was definitely learning things, okay? But when we have classification for 39 classes that are not balanced, using things like accuracy can be not necessarily deceiving, but it might not be necessarily the best metric. Now, it's hard to come up with a good metric, honestly. We decided to stick with what is called the Matthews correlation coefficient that takes into account different values in the confusion matrix. Now, the way to kind of read this is you kind of want to read it in vertical kind of lines. So because this is a bit normalized, all right? It's just that I think plus and minus 2, the values, there were way more values than say, plus and minus 19. And then it was kind of harder to read because some of the circles would have been like way larger. So this is a bit normalized in the sense that if you just stick with one kind of vertical line, it tells you based on the true value. So maybe let's stick with 0 for now, right? It has a big circle in the middle. It means that most of the time it predicts correctly 0, right? And very rarely it predicts other values, okay? Now here maybe at 15, you'll see that actually it predicts 15 and minus 15 roughly the same amount of time, and occasionally it predicts minus 5 maybe. It never really seems to predict 0, etc. Okay, so that's the normalization. Yes?
Can I ask, does the distribution of values, you said that 2 and minus 2 are most common. Does the distribution of values like roughly track what we theoretically know to be the distribution of the A97 for random partial forms?
Sure. Yeah.
Saute distribution.
Okay.
With line, your values are so small, you also need to mind trotter. That's why 2 and minus 2 are more common than 0, but.
Okay, yeah.
Another interesting quantity would be the cross entropy of the prediction.
Okay.
Yeah.
The cross entropy. All right. Yeah. Yeah, we were looking at a few different things, but oh yeah.
From this, it looks like it's much easier to predict the absolute value than the sign.
Yeah, exactly. So let me see if I'm going straight to observation. No, okay, not yet, but I'll give some tables with how well it did to predict the absolute value. And it's not, so here you can see kind of that the circles for 2 and -2 are kind of larger. So it's still like, even after, I think this was 200 epochs, it, that took a while, okay? Because one epoch was basically going through all the data. Even after 200 epochs, it seems like very often it does default to kind of the largest class. But sometimes if you kind of squint from like the right distance, you can almost see kind of like little diamond shapes, like bigger circles this way and like a smaller circle there, that kind of like a spoiler, it does very well predicting mod 2. That was one of the things. So like so these little diamonds kind of play with that. Yeah.
Maybe I'll follow up on the previous question. You try to predict the sign.
Did I try to
Sort of
predict the
split.
sign? Yes.
The prediction of the piece into the sign and the magnitude. Maybe that.
Yes. Yeah, we did. It didn't end up in the paper. But for this particular one, I think because the sign ends up basically being binary classification, because there's very few times it's 0 and plus and minus are roughly 50-50. I don't have a figure off the top of my head right now. I think it was about 70%. But yeah.
I was kind of wondering because maybe you can decouple predicting that the coefficient into the sign and the magnitude. So you should be doing way better for the magnitude.
Right. Yeah. So I'll talk a bit about something like this later in the talk. Basically, well, actually, no. I'll get to that a little bit later. Yeah.
Is 70% improving on what you already have here? Because the circle along the diagonal look better, bigger than the circle along the anti. So do you already have 70% of the site correctly?
I believe so. Yeah.
Okay, so the predicting the sign did not improve.
Sorry?
So splitting the absolute value and the sign does not improve on predicting the two together.
Oh, I see what you mean. So the 70%, sorry, let me get back to that, just make sure that I said things correctly. 70% was just predicting the sign. We did do experiments predicting just the absolute value. And then I think I did try to like, okay, multiply the two of them together. What does it give? But I don't remember if it did better or worse, or ultimately the input is kind of the same data. So.
But it seems to decouple the two. I mean, thank you for the follow-up questions. But yeah, I mean, it looks like if you flip this diagonal onto the other one, I mean, now you're at 53, you would get very, very high and then multiply by 70% accuracy for the sign prediction. It looks like you could do better than 53%.
I doubt it, but I mean, yeah, it's possible. We have those experiments somewhere. Yeah.
This already looked like to me like you've got 70%.
Yes. Yeah. Yeah. So also, yeah.
Okay, I see.
I don't remember it doing like way better, but it's possible that it is an improvement. Yeah.
Curves probably include lots of curves that have like a 2 torsion point or some other unusual Galois structure, right? Wonder what happens if you remove those or.
Oh, okay. Yeah. So sorry. I should have said that this is not on the whole data set of 3.6 million because we just looked at the curves with the good reduction at 97. That's kind of why I'm reporting on A97 because we also looked at predicting A2 and A3, but then taking just the curves with good reduction at 2 and 3. Again, it shrunk our data set by a lot.
Yeah, but that's a different question. What I'm
Right.
imagining is for low conductor curves, unlike typical elliptic curve, it's quite common that you have rational tree isogeny or some two torsion point, and the first dozen or so APs are thorny enough to, if not detect, then make it very, you know, thorny enough to exclude the possibility of there being two torsion, usually enough to detect that there is one there. And that gives you a lot of information about any further case of P, and I'd expect that any of these models would pick up on that a lot before they did anything mysterious. So I'm wondering if, I'm sorry if I'm repeating something that was said already because I didn't get up early in time. So I'm wondering if this effect would persist if you removed curve that had, you know, particularly small Gauss representations.
Yeah, we haven't tried that. We kind of used as much as we could from the data set. But I mean, that probably will affect.
So I think it's often, well, maybe not for A97. Never mind what I was about to say. Sorry. I leave it at that. Sorry.
It's all good. I mean, it is true that I guess it seems like the conductor is large, but it's not that large, right? So it could be that curves of small conductor obviously don't behave like any random curve you see out there. So, but yeah, we haven't tried that. That's maybe for the future. Okay, so I want to just give some tables with the accuracy, well, the performance if we're just looking at the absolute value, and then if the performance of the model, if you're looking at, you know, take the prediction and reduce it mod 2, right? Reduce it mod 3, reduce it mod 4. Those were some things that we tried out, and then we noticed that indeed it does pretty well mod 2, to a certain degree mod 4, mod 3, not much better than you know, what we would expect. So to just kind of give you a definition in the big sum that you probably can't read in the back, the Matthews correlation coefficient has generally been used for binary classification if the classes are not balanced. But there is a generalization to multi-class experiments as well. So big sum, complicated terms, but basically the terms that show up here are the entries in the confusion matrix. So in a way, it considers, if you're thinking of binary experiments, right, true positive, false negative, all of that stuff. Now, if you have a 39 by 39 confusion matrix, it takes into account all of those values. All right, so some of the results. Now, the experiment that I told you about was for predicting A97, so that's the third row. We also looked at predicting A2, given, you know, all the other traces of Frobenius A3, A5, all the way to up and including A97. So in each case, the input was of length, you know, 24 traces of Frobenius, and then we're predicting a missing one that lives nearby. All right, so because we did just look at curves with good reduction at the prime P, for predicting A2, we only had 700,000 curves from that data set. For predicting A3, we had a little bit more. You know, by the time that you're looking at primes like 29, 31, et cetera, you get a fairly big share of the data set. When we're looking at 97, we had 3.5 million in the training set. In each case, for the test set, we took 10,000 curves that were not in the training set. So maybe we're not using, like, you know, the rule of like 20% training, 80%, sorry, 80% training, 20% test, and maybe some validation and whatnot. But we thought, well, hopefully 10,000 curves will give us a good idea of how the model performs. All right, so we trained each of these experiments for 200 epochs, 1 epoch for basically the whole data set. For predicting A97, we had 39 classes. For predicting A3, it goes between -3 and 3, so that's 7 classes. For A2, between -2 and 2, so that's 5 classes. Basically, this is the absolute value when I say sign agnostic. Maybe I should have just said absolute value, MCC, right? So it does jump. It's not like saying 73% accuracy because it's a different metric, but I don't think it's necessarily wrong to intuitively kind of think of it the same way. Then, if we take the label that is predicted and we reduce mod 2, all of the experiments do way better than the initial experiment. Mod 3 actually does fairly comparable. Okay, mod 4 does a little bit better, not as well as mod 2. Obviously, it includes the information mod 2 in a way, but it still does better than just the original experiment. Okay, so let's see. Any questions about that? Yeah.
Do you have any reason why mod 3 would be worse?
Try to interpret as much as we could, and we want to be very cautious to really say anything really. I have my suspicions. So I'll talk in a couple of slides that, right, when we did the prediction mod 2, so we just took the data set, the APs, reduced the mod 2, fed them into the computer, and then we realized that there were way fewer training examples than the initial 3.5 million. And what also ends up is that once you reduce mod 2, a lot of the training examples, those mod 2 end up in the test sample as well. Initially, all of the training examples are distinct, but once you reduce mod 2, there were things in the test set that we've seen in the training set. Okay, so it's kind of like, well, you can't really run an experiment like that, right? So with mod 3, something else that we know, that I don't have the numbers right now, but it did seem like it was way better at predicting whether A97 was divisible by 3 versus not than predicting the exact residue class. So I'm thinking it, I mean, from, I don't know, maybe the elliptic curves experts can chime in, but if we are taking the data and now don't just reduce it mod 3, but we just have a 1 if it's divisible by 3 and a 0 if it's not, again, we kind of end up with overlap in the training and test set. So maybe that's, so it does well there, but to get back to your question, it might not be very good at distinguishing like 1 mod 3 and -1 mod 3, kind of the way that it wasn't doing very well distinguishing the sign. Sorry, that was a very roundabout answer. Yeah. So those are kind of my suspicions that maybe there is this overlap in the training and test set if you're looking at divisibility by 3. But it's not clear to me, like if you know whether the, say you know enough AP, well, 1 million APs, and you know if they're divisible or not by 3, should you be able to predict whether the next one is divisible or not by 3? Like if you know the residues, I know for a fact, like if you have enough, you should be able to, but just by divisibility, I don't know.
Does the same thing happen with 2, but it's better at figuring out whether it's divisible by 2 or not?
Yeah, right, because mod 2 is the same as divisibility by 2, right?
Yeah, that I asked.
So can you repeat the question?
I was asking if it's the same thing with, mod 2. It's like, yeah, because the two of them are kind of the same.
I guess the sensible question would be for larger primes, if it does that, like if it's better at predicting whether it's.
Well, for larger primes, it's kind of hard to really, because the larger the prime, the less likely that the AP is divisible by that prime, especially like for the obviously smaller ones because of the bounds on the AP coefficients. So it kind of just basically tells you if it's 0 or not.
Did I understand correctly? You said there are different elliptic curves with p equals 2 through 97 mod 3 that have the same vector mod 3. So you said there's a sort of train set and test set sort of doesn't overlap, which means that there are two different distinct elliptic curves and nevertheless have sort of the same vector mod 3.
Well, yeah, the first like 24 or whatever.
Yes, for p
Yeah.
equals 2 to 97. So are there then also curves that are the same for the first 23 and then have a different A97? I mean, it's the theoretical predictability still 100. I mean, it's the best you can do still 100%, or is there sort of other contradictions in the?
Right. Oh, so, we definitely looked at some of this stuff, but I don't know if I remember. So if we're taking like small, right?
Yeah, no, I'm just saying, so it could be that sort of the input vector is the same, but yeah, sort of the target is different.
Yeah. Oh, sorry. Yeah, we also had that issue. Yeah.
What did you do? You removed them?
Let's get to that. I think it's is it in the next slide? Yeah, it's coming up. Okay, so I'll do this quick so we can get to your question. Right, so we were thinking, okay, it seems like the models are doing very well, predicting A97, whatever mod 2. Well, in fact, if you just give it the APs, it predicts, A97 mod 2 just a little bit better. The other thing is that, well, once you take the reduction mod 2, even if you kind of feed the model just the reduction mod 2 data, even if you probably shouldn't have, experiments with overlap in the test and training set, it does pretty much just as well as these numbers, mod 2. Okay. So then we say, well, we should really be trying to feed it distinct training and test data, but we had to expand our data set. So we looked at curves with conductor up to 10 to the 7. So, right, we had the duplicates, etc. Even worse, it was not uniquely determined. So we did kind of remove them. We didn't really know what's the best way. I mean, I don't know. Kyu-Hwan, we had a lot of conversations about what's the best way to kind of like handle this. And I don't know if we came up with like a good solution.
Oh, unique solution.
Yeah.
Trying to possibilities. Not all, but we tried many options.
Yeah, it was. Yeah, like if you have to, say you have 10 training examples where, they're all the same once you did everything mod 2 and they predict 0, right? And then you have 5 of them, right? And it's the same training example, but it predicts 1, right? Then what do? Do you remove like 14 of them and just keep like a random one? Or do you try to kind of weight things in a way? Or, yeah, that's still something that, we haven't come up with a good solution yet. I think for the following experiment, we kind of just kept the first instance based by conductor. Yeah. So it might not have been the best choice, but that's kind of what we did. Yeah.
This is very naive, but for this experiment, don't you have like something like 16 million different inputs and you just generate them all? Like you assess that, for example, the duplicates and what to put in the training and whatnot. So you have 24 numbers that are 0 or 1.
Mm-hmm.
This is about 16 million.
Well, if they were random, so there's a lot of possible options.
Recompute everything. I don't know how difficult that is, but it's like on the order of tens of millions. And then that will give you a better feeling of like, what do I do with the duplicates? What do I do with, I don't know, these sort of non-uniqueness problems and so on.
So some of the reviewers did recommend that, well, we could try to do an unsupervised learning experiment where we're kind of feeding like the whole sequence of like, mod 2 and then, mod 2, for example, and then see if we can, sorry, I have like 2 different comments the referees had right now, kind of mixing up. So sorry, one of them was, can we predict which one corresponds to an elliptic curve if we have both things that are, we generate random zeros and ones, right? 24 of them, and then we have those coming from elliptic curves. Can we predict which ones are coming from elliptic curves? Or maybe some unsupervised learning experiments where maybe we can, I don't know, maybe feed the whole sequence and just see what we notice from that. But we haven't really had time to really try that out. But yeah, we had way fewer mod 2 examples than I initially expected. Personally.
But in the end, are you saying that for predicting a 97 mod 2, you do know better if you have the full set of AQs up to 97 versus just having them mod 2? So is it true that all the information that you're actually getting for a 97 mod 2 is really just coming through the reductions of the AQs mod 2? Is that what it seems to be? It seems to be like the performance is very comparable. Yeah. Okay. So it seems that then all the whatever phenomenon this machine learning is detecting is really just a question about what the action of the Galois mod 2 toward mod 2. Right. So it's really just the question of the action of Galois on a little whatever a number field. It's really now not an elliptic curve question. It's really just the question about that extension that generically is an S3 Galois extension of Q, and you're looking at how the Frobenius elements act on that, and then that's really what it's detecting. Yeah, which I guess we did start out with the experiments to predict A97 mod 2 from the reduction mod 2, and then we kind of like went back full circle at predicting A97, and then so it does seem like the model probably does predict A97 mod 2 just from the reduction mod 2, right? Yeah. And then that kind of leads to the question of should we have even fed like all of the APs together to begin with, right? If maybe we can separate it by primes, right?
This suggests another experiment which we to destroy the mod 2 information by adding something random mod 2 and see if the predictivity goes to 0.
Right. Okay. Yeah.
An unrelated question. Do you have any idea why the 5 is so hard? Am I reading this graph correctly?
Yeah. So let me describe what's happening here, because so far I told you the prediction for A97 mod 2. Then we ran predicting AP for all the primes. So basically, we took there's a vector of length 25 for all the primes up to 97. Then we removed one, so we're left with 24 of them. Predict whatever we removed. Okay, so it's not clear if there was also something about 59, 73. It's I don't know. For these ones, maybe it's just we push the button. Maybe it stalled somewhere. Maybe for 5, it actually has some reason to struggle. It's not clear. There's 2 questions, but Jordan, yeah.
Just a quick question about this graph. Are all of these trained up to 10 to the 7? And you have these 3 ranges. Are those different tests or are those different trainings?
Okay. It's one experiment. So we fed, I think it ended up about 5 million elliptic curves conductor up to 10 to the 7 once we took the reduction mod 2. But in the test set, we divided up into like 3 different parts for different conductors. So it's one experiment. It's just this kind of tells you the performance for each conductor range. Yeah. So obviously a smaller conductor does better, but not even close to, what we had earlier. And then for the larger conductor, it barely learns anything, kind of. Well, I guess I don't have a very good definition of barely, but basically, if it's at 0, it predicts things randomly, and it kind of like goes between 0.1 and 0.2 for the higher conductor range. Okay. Let's see. So this was for mod 2. We also saw that it seemed like it was predicting things pretty well mod 4. It kind of includes the information mod 2 in the mod 4 reduction. But something else that as we were kind of visualizing, especially the kind of initial embedding. So that's when it kind of learns how to group the different tokens near each other. So technically, it's a larger dimension vector space, but then when we take the two-dimensional principal component analysis and we look at it, then we see a pretty nice picture. Like, I really liked it. So on the one hand, it seems like the plus and the minus tokens are smack there in the middle at 0, 0. It doesn't really learn to distinguish them at all. Now, for the first component, it's dividing up the APs whether they're divisible by 2 or not. And then for the second component, it seems like it's grouping whether it's divisible by 4 or not, except for this 0. Yeah. Usually they do kind of like hang around a little bit more together. I think this was for a specific epoch that I took this screenshot. Yeah.
How much of the weight is in these first two components?
Yeah, I should have included that. Yeah, I don't remember.
But most of it, or
It was. No, it wasn't. It wasn't most of it. No. So again, it's kind of keeping 1 and 3 mod 4 almost. It doesn't really learn, at least in the embedding, to distinguish among them. So one of the kind of follow-up questions that I've been just trying to run some experiments since we've submitted our paper was, well, at least from that picture here, right? Sometimes we can notice like little diamonds, but we don't really seem to notice things like mod 3. I mean, those would be kind of harder to notice if it's predicting things well, whether they're divisible by 3 or not. So mod 2 is one thing. But if we could potentially separate this into like smaller experiments where we're just giving it the information like, mod 2, or, mod powers of 2, powers of 3, maybe powers of 5, if we patch that up, will that give us something that's looks like a similar picture? Can we figure out what this model eventually has been learning? So is it learning based on mod information, modulo small primes, or is it learning based on divisibility by primes? Maybe it's learning based on magnitude. We don't really see that from the picture, but that was something that I was interested in, and I just ran a few experiments, so I'll probably just in the next 10 minutes show you some more pictures. Okay, so I ran a few different experiments, and people will probably be pretty grumpy about this, but okay, so a few experiments where it was predicting A97 mod 3 from the mod 3 reduction information, mod 4 from the mod 4 reduction information, mod 5 from mod 5 reduction information. Now, if you're using the Chinese remainder theorem, then you have 3 times 4 times 5, that's 60 options, way more than the 39 options that we have. So sometimes it might predict something that's not in the range, and you have to kind of figure out what you're doing with those examples. Same thing if you're predicting mod. So I looked at mod 5 and mod 8 simply because I wanted something that had like a closer number to classes. In this case, it's like 40 as opposed to 39. It's easier figure out what happens to the extra class, then if you have extra 20 classes. And then finally, 2 experiments where it was predicting the valuation at 2 and, kind of the unit away from 2. So I don't think you really need to read kind of what's in the small text, but this is the kind of original experiment picture, okay? This is patching up the prediction mod 5 and mod 8 and putting things together. Now, what happens if it's predicting something like, once you give the information mod 5, say it's 1 mod 5 and minus 3 mod 8 or something, and 5 mod 8, that would predict 21. That's outside of your range. You can either throw it away. I think for these examples, what I did was that those experiments were often predicting the negative value. It wasn't good at predicting, value versus the negative. So if it was giving me something outside of the range, I would flip the mod 8 to the negative, or the mod 5 to the negative. So it's kind of ad hoc. It might not be the best way to patch things up. For the prediction, this is for the valuation at 2 and value, the unit away from 2. There, I think if it was predicting something outside of the range, if it was giving me a large power of 2 and times 17 or something like that, I think I would just send it to 0. And this is patching up 3 experiments predicting mod 3, mod 4, and mod 5. So what did I want to get out of this? I was curious if I patch a few of these different experiments that have kind of mutually disjoint information, can I get a picture that looks similar to this? When we're doing the mod experiments, we get a lot of grids. It looks very nice, but it doesn't necessarily look very similar to this, although we still notice the value, it's predicting the absolute value still pretty well. For me, at least, it seemed like this picture maybe looks more like that than the other ones, although a lot of these values kind of cluster on like the smaller ranges here.
Can you wrap up soon?
Oh yeah, sorry, how much? 3 minutes? Okay,
Time
yeah.
for questions.
Okay, yeah. So I'll go through, I think I just have 2 more slides. So, okay, A97, there's a lot of prime divisibility, right? Because you have 2, 3, 5, 7, 11, 13, 17. I don't even know what to do with 19 because up to A89, none of them take the value 19. So somehow it's still learning to predict when it is 19, but it's not clear why. I looked at kind of patching up similar experiments, but now for predicting A29, that goes between minus 10 and 10, so it's fewer primes. So I was looking more at kind of the patching up multiplicative experiments, so predicting valuation at 2, at 3, at 5, at 7, and here I took the sign, so to kind of get back to one of the questions from earlier. Now, with the sign, it just predicted randomly. I guess we kind of expected that. If you're just giving the sign at AQ, at the different A primes, it shouldn't predict the next sign. I think they should be more or less equidistributed. But then there was another experiment that had the sign at A29 times the valuation at 2. So I was thinking, will that do a little bit better? So just to kind of show you, this is the original experiment predicting A29. This is if you're patching together the different valuations at 2, 3, 5, and 7, and the sign, but the sign is kind of predicting it at random. And this is for the same valuations at 3, 5, 7, and the sign times the valuation at 2. So that was one experiment. So kind of conclude, I don't know if I have really an answer. Is the model really predicting based on divisibility? It's possible, but it seems like neither of these pictures really looks like that. So it probably contains it needs some of the other information. Okay, then I'm done.